What if there was a crowbar, a light year long, floating in space? Why do the sun and the moon look so big close to the horizon? And how do we measure temperature in space? Answers to all these questions and more in The Question Show. It's time for The Question Show. Your questions, my answers, as always, wherever you are, across my channel. If a question pops in your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Alexander Glimt 3945. How do you measure temperature in space on the moon where there is no molecules in space that get warm or cold? Does it not depend on what surface you are measuring on? For example, black, white, or reflective surface. What is stated that it can be 120 degrees Celsius on the moon? What is it that has this temperature? Right, so whenever you say that the temperature of space is whatever, 2.7 Kelvin, or 120 degrees Celsius, or 2.5 million Celsius, then you'll have people going, whoa, wait a minute. You can't say that space has a temperature because the temperature is caused by molecules, and the molecules are the ones that are actually giving off the temperature. Space itself, the vacuum of space, has no temperature, and that is technically correct. So if somebody says, well, what is the temperature on the moon? They're not talking about the vacuum that is above the surface of the moon. They are talking about various things which, placed at the distance from the moon to the sun, what temperature will those be? And you could measure the temperature of them. You could take a thermometer and you could touch it to a rock in space that's in sunlight, and you could measure that temperature. And you could point an infrared thermometer at a rock that's sitting in space, and you could measure the temperature on that rock. And there's another thing called a bolometer, where you can measure the electromagnetic radiation that is coming off something, if it's giving off temperature in other wavelengths. So, when you were talking about the temperature in space, you're talking about the temperature of the object itself. And you're exactly right that, when you think about what it's like to walk on a black sand beach, like your feet get really hot, or walk on the concrete or whatever, very different from the temperature that you feel when you walk on something that is white, that is cool. And even though they're both receiving the same amount of radiation, they're going to be different temperatures based on how reflective they are, how much they absorb the light, how much they're able to radiate the heat away. In the case of Earth, right? How, what other methods are extracting heat from them? Are they wet? So on and so forth, right? So that is like a sort of an idealized temperature. You're calculating the temperature that an average thing would be based on the amount of radiation that is falling on it from the sun. But the actual specific individual temperature of an object is going to change. And it's really amazing. Like on the moon, when you're in the sunlight, if you have a rock and you're measuring the infrared, thermometer on the surface of the rock, on the face of the rock that is facing the sun, you're going to see 120 Celsius. But then if you go and measure the shadow side of the rock, well, it's not going to be exactly. It's going to be about negative 130 Celsius. And that is just because the second you don't have that sunlight, then temperatures drop significantly. Now, with the rock, you're going to have the side of the sun face is going to warm up, and so it's not going to be as cold. But, in the shadow of the moon, in the places on the moon that have never received sunlight, the temperatures get very, very low. And so, whenever you ask, what is the temperature of space? You got to specifically say the temperature of the thing that you're talking about, not space itself. Paul Holt, I feel like we can see more of the Milky Way from the Southern Hemisphere. Is that right? It just depends on where you are on the Southern Hemisphere. So where I live in Canada, I can see the Milky Way. The Milky Way at various times of the year goes like directly overhead from my place. So I see, Milky Way from horizon to horizon. But the heart of the Milky Way, the place that has a lot of the most interesting stuff, the place with all the dust lanes and the very center of the Milky Way, is in the constellation of Sagittarius. And for me, that is always very low on the horizon. Sagittarius only appears in the summertime for me, and just gets above the tree line, above the mountains that surround me, and then I can actually see some of the objects at the center of the Milky Way. And then a couple of months later, it's dipped back over under the horizon, and then that's it for me for another year. But the one time that I was in Australia, we were just north of Brisbane on the east coast of Australia, and we were in a place with really dark skies, and the Milky Way was directly overhead. But the core of the Milky Way, the heart of the Milky Way, was directly overhead. And in fact, a bunch of the planets, for me, the planets, again, are sort of in this line off towards just above the horizon in the south for me. But when I was in Australia, the planets were directly overhead. I looked up, which then that minimizes the amount of atmospheric haze between you and what it is that you're seeing. And so I think it's just that it looks so much better from the Southern Hemisphere. And especially, when you're just slightly south of the equator, then it looks like really amazing. But as you continue south, as you move towards Antarctica, then you will probably see the center of the Milky Way start to be harder and harder to see, and so have sort of a similar version to what I do. So the best skies I've ever seen were in Australia. So I think just there's really good dark skies in the Southern Hemisphere. Hooves. What is metallic hydrogen? So metallic hydrogen is essentially what you get when you put hydrogen under enormous pressure, and not just like put it in a vise, but like put it in the heart of Jupiter. And so when you think about Jupiter is actually this enormous, massive blob of hydrogen and helium and other elements that has, it is essentially the mass of all of the planets in the solar system, right? Like most of it is in Jupiter, and all of that mass is pushing down and causing this incredible pressure. And, at the high points of Jupiter, when you're close to the cloud tops, then it is like this light fluffy gas. But as you go deeper and deeper, then the pressure increases, and eventually it's like as dense as water. And then it's as dense as iron. And eventually you get this form called metallic hydrogen. And it's never been directly observed because it's trapped down in tens of thousands of kilometers of Jupiter. But we know that Jupiter has this incredible magnetic field. Very powerful. And this is caused by hydrogen that has been turned into a metal. And then the metal acts like a dynamo at the heart of Jupiter that is then sort of rotating and generating this enormous magnetic field in the same way that we have a rotating ball of liquid iron at the middle of the Earth. Jupiter has a rotating ball of metallic hydrogen that is causing that. And there have been some recent claims that people have been able to actually make metallic hydrogen in the lab. And so I say, well, you can't just make it in a vise, but in fact, that's how they make it. They make it in a vise. They have this thing called a diamond vise where they're able to concentrate enormous pressures at the very tip of this vise. And they have claimed that they've been able to actually make metallic hydrogen. They're able to crunch hydrogen down to the point that it actually behaves in that same way as the stuff that's down in the middle of Jupiter. And it would be a game changer. Like if we actually could produce metallic hydrogen, then it is an energy dense fuel like nothing we've got down here on the surface of Earth. And so you could have spacecraft that could just like take off, land, right? And you wouldn't have to have like giant refueling. You wouldn't have to have booster rockets, all that kind of stuff. It's just that the fuel would be so dense, it would be able to allow you to get around the solar system. It's sort of in the way science fiction has always told us it should be. But the other thing is we just don't know if metallic hydrogen is stable. Like when you force metallic hydrogen down into that form, does it just remain? Can you then remove it from the vise and then put it in your, I don't know, in your spacecraft and have it sit there until you need it? Or will it immediately want to expand back out into a liquid form or a gaseous form as soon as you take the pressure off? And so like, can you maintain the pressure inside your spacecraft to keep the metallic hydrogen tiny and dense? Because like if your containment doesn't work, then the thing will detonate your spacecraft. So metallic hydrogen is really exciting, and I'm really looking forward to more research as we, people attempt to recreate this in the lab. Not only because it could be a potential source of storing energy, like the best possible battery, but it also teaches us a ton about what's going on inside worlds like Jupiter. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Three Dog, Leonard Kroll, Mike Palan, James Clark, Rupert Millard, and Roy Else. Join the club at patreon.com/universetoday. M. Why is it that when the sun is rising, it's bigger and more colder and cooler than when at 1 p.m. the afternoon is smaller and hotter? So this is an illusion. The sun is not bigger when it's at the horizon, when it's rising or when it's setting, than compared to when it is high up in the sky. It is exactly the same size. And the same thing goes for the moon. Like, have you ever gone out and the moon is just rising and the moon looks enormous? And then later on, you go outside and you look up and the moon is teeny tiny and you're like, wow, why is the moon so much? Isn't it crazy that the moon looks so much bigger when it's on the horizon than when it is high up in the sky? Well, the reality is it is exactly the same size. And this is a weird trick in our brains called the moon illusion. And I guess there's also the sun illusion. Why does this happen? We don't know. But it seems that it has something to do with when we see something like the moon, where when it's high up in the sky, our brain kind of has no context. And so it sees it in the size that it actually is. But when it is down near the horizon, you're seeing it compared to buildings and mountains and trees and things like that. And so your brain tries to size it based on what it knows to be the sizes of those other things. And the way to show that this is really just an illusion is check out the size. And the one that I like to use is your little finger, your pinky finger, nail. And the moon and the sun, but with the sun, you'll hurt your eyes. But with the moon, it's safe to do, because they're the same size in the sky. But the moon is the size of your pinky held at arm's length. So you hold out your hand, right? You look up at your pinky and you hold your pinky next to the moon, and you'll see that it is exactly the same size as the moon. And then do this when the moon is down at the horizon, and then wait many hours or another night, wait, and then do it when the moon is really high up in the sky. And you'll find that they are exactly the same size. And there's great pictures that have been taken where you can see the moon. They take a new exposure of the moon every couple of minutes. You just get moon, 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 and it stays exactly the same size. And same thing with the sun. So yeah, your brain is lying to you about the difference in the size. Shalab Mehta. Gaia's role in the distance ladder calculation? ? Gaia is one of the most important roles in the distance ladder. It is the foundation of the distance ladder. And so, if you don't know what the distance ladder is, this is this way that astronomers measure distance in the universe. And there are methods that work very well for things that are relatively close to us. There are methods that work well for things that are farther away from us, and then farther away from us, and then farther away from us. And then the trick is that all of these different methods overlap with each other. And so you can use them to double check one another. And this idea of using the distance ladder goes all the way back, more than 100 years, back to when... was it Vestal Slifer? Right. So we knew that the parallax method allowed you to measure the distance to various stars and calculate how far away they are from you. But that only gets you a few thousand light years away from the Earth before the distances that these stars are moving when you're on one side of the sun to the other side of the sun is so small that you can't measure it. And so you can't measure the distance to that star. And so there's this like sphere of radius around the Earth where the distance ladder begins and starts with the parallax method, and then it maxes out. But fortunately, there's a type of star called the Cepheid variable, and they are closer than the parallax method ends. But also these Cepheid variables are very large, very bright, and they're visible not just in the Milky Way, but even in other galaxies. And so you can double check. You can calculate the distance to a star, a Cepheid variable, using the parallax method with Gaia, for example. And then you can measure the intrinsic brightness of the Cepheid variable, and you can use it to calculate what its distance is, and you make sure that those two distances are the same. And then now you're measuring Cepheid variables out into Andromeda and into other galaxies. And that's what Edwin Hubble did to measure the expansion of the universe. Was he was measuring the redshift of various galaxies that had these Cepheid variables in them. And then the next overlapping thing is type 1a supernova. And then you've got the cosmic microwave background radiation. And there's a whole bunch of other distance methods. There's about 20 that you can measure, and they overlap. And so you can sort of build up this distance ladder that gets you from here to 5-6 billion light years away. And then there's this gap. And then you've got the distance of the cosmic microwave background radiation. And so the astronomers are really trying to figure out that gap between the CMB and where the type 1a supernova end. But Gaia was the foundation, and by providing the most accurate parallax measurements that have ever been provided, it fine-tunes the entire distance ladder because the rest of it depends on the parallax method. Alex Patulny, how long is it physically possible for a crowbar in space to exist, especially if no other matter were to get in the way? Could you have one a light year in length? So are you asking how long physically would a crowbar last in space? Or how big of a crowbar could you make? So I'll tackle both of those questions, I guess. How long would a crowbar physically last? We don't know. But when we think about, say, the Voyager spacecraft, they have the golden records on them, and the golden records are in a protective case. And it's believed that the golden records should be playable about, say, 500 million years from now. I mean, they're going to be constantly eroded by space dust, by cosmic radiation, they'll be worn down, and yet they'll still be playable that far into the future. So you would be looking at billions of years. You know, if you had a crowbar that's made of metal, it's going to be getting hit by cosmic radiation, by space debris, dust, things like that. It's going to get worn away. Eventually, it'll just turn into dust. But you're looking at billions of years before your crowbar erodes away. How long could your crowbar be? Could it be a light year in length? So the problem is it depends on how much material is in the crowbar. If you have a crowbar that is like the thickness of a regular crowbar, it's not very big, it's not very thick, and yet you're going to have this thing be a light year in length. Any kind of gravitational disturbance is going to start causing ripples in the crowbar, that it's going to start to bend and torque and twist in various directions as it is attracted to various objects of gravity across 1 light year. And I think eventually you're either going to twist up your crowbar a bit, or just it's going to flex back and forth enough times that it's going to start to, the metal's going to break and your crowbar is going to float away into multiple pieces. So it can't last forever, but it could last for a while. All right, those are the questions that we had in this episode. Thank you everyone who put your questions into the YouTube comments, and everyone who watched us live. We record this show live every Monday somewhere in the world at 5 p.m. Pacific. So there will be a link to the upcoming time. I think the next one is in Europe, 5 p.m. European time, but you have to double check. All right, I'm going to chat about an exciting new telescope that we have access to for the Star Parties. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Bear Lake Roofing, David Gilton, David Matz, Dennis Alberti, Dustin Cable, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Robach, Sean Sargent, Spiderswap.io, Stephen Fowler Munley, and Vlad Chiplin, who support us at the Master of the Universe level. And all our patrons. All your support means the universe to us. So we've been doing these test star parties leading to the full return of the virtual star party, where we have a bunch of telescopes and a bunch of astronomers, and we are showing live views of the night sky. And sort of the bedrock part of this is that I have access to an incredible set of telescopes from Starfront. And this is a telescope co-location facility down in Texas. And the one telescope that we've been using is this Celestron Origin, which is really great for doing deep sky observations, nebulae, galaxies, clusters, things like that. that. It has a very wide field of view, but it can't see things that are small in the sky. But the best things that are small are the planets. And so Starfront has set up a second telescope that we're now able to use. And this is a dedicated scope just for planetary. And so now we can show you Jupiter, Saturn, Mars, craters on the moon, the Venus, and maybe even Mercury. And so it's going to be an exciting new time. And so we're going to be doing a bunch of tests this week, and then we're going to be folding that in. And at that point, everything should be ready for us to bring back the virtual star party. So stay tuned. There will be random live streams with me in the telescope this week, and then we'll move into a more regular schedule. But it's really exciting. It's very cool to see with this new telescope. All right, we'll see you next time.